Hello, let us start chapter 5, module 8. Ultimately, in this module, we are in a situation to prove classical version of Ascoli-Arzelà theorem. To prove Ascoli-Arzelà theorem, first we require the notion of equicontinuity. So, what do we mean by equicontinuity? Let X and Y be two topological spaces and let Cxy be the collection of all continuous functions from x to y. Now let us consider a subset of Cxy. Let us name it as script f. Then script f is said to be equicontinuous at a point x belongs to capital X if for any given epsilon greater than 0 there exists a neighborhood U of small x in the topological space X such that for any y belongs to capital U, f of y is situated at a distance less than epsilon from f of x. That means we can say that all of the members of script f is continuous simultaneously. We shall describe this much more in our presentation. So let us go to slide presentation. As we have said that our aim is to find compact subsets of the space Cxrn in the uniform topology. We shall require the previous theorem for this purpose. That means X is compact if and only if it is complete and totally bounded. One might hope a result for Cxrn and analogous to Bolzano-Vassas theorem, but it does not. Even if X is compact, one needs to assume that the subspace of Cxrn satisfy some additional condition which is in fact our equicontinuity. So let us start with the formal definition of equicontinuity. Let Y D be a metric space and X be another metric space. Let script f be a subset of the function space Cxy. If x0 belongs to x, then script f of functions is said to be equicontinuous at x0 if given any positive number epsilon there exists a neighborhood U of x0 such that for all x belongs to U and all f in script f, distance of fx and fx0 is less than epsilon. If script f is equicontinuous at x0 for each x0, it is simply said to be equicontinuous. So, if script f contains finitely many functions and each member of script f is continuous, which is obvious, then script f must be equicontinuous, because for each member of script f we shall get a neighborhood, say uf. Now since we have considered script f finite, we take finite intersection of ufs, which is again an open neighborhood containing x naught, and this intersection will work for all members of script f. Hence, any family of finitely many continuous functions is of course equicontinuous. Note that equicontinuity depends on the specific metric D rather than merely on the topology of Y. We need the following lemma to prove our Ascoli-Arzelà theorem. Let capital X be a topological space and Y D be a metric space. If script f be a subset of the function space Cxy is totally bounded under uniform metric, then script f is equicontinuous under D. That means, as Cxy is a metric space under the uniform metric, if script f is totally bounded under this metric, then script f is equicontinuous under the metric D. To prove this, let us consider script f be totally bounded and epsilon be a positive real number which is strictly less than 1. Let us choose some x naught in capital X. So, to prove script f is equicontinuous, we have to find a open set containing x naught such that for any f in script f and any x in that open set U, we have that distance of fx from fx naught is less than epsilon. Now let us set delta is equal to epsilon by 3 and let us cover script f by finitely many delta balls, say bf1 delta, bf2 delta up to bfn delta in Cxy. Why we can do this? Because script f is totally bounded and hence it has finite epsilon net for any positive real number epsilon. So, for positive real number delta, script f must have a finite delta net. Here that finite set is f1, f2, fn. Now each function fi is continuous. Therefore, we can choose a neighborhood U of x naught such that for each I is equal to 1 to n, distance of fi x to fi x naught is less than delta whenever x belongs to U. Let f be an arbitrary element of script f, then f belongs to at least one of the above delta balls, since the above delta balls covers Cxy, say F is contained in Bfi delta, then for x belongs to u we have d bar fx fix is less than delta, d bar fix fix naught less than delta, d bar fi x naught fx naught less than delta. The first and third inequalities hold because rho bar fi less than delta, and the second holds because x belongs to u. Since delta is less than 1, the first and third also hold if d bar is replaced by d. Then the triangle inequality implies that for all x belongs to u, we have distance of fx from fx naught is less than epsilon as desired. Now, to prove Ascoli's theorem, we shall require another lemma. This can be considered as a partial converse to the preceding lemma, which holds when x and y are compact. Let capital X be a space and YD be a metric space. Assume that x and y are compact. If the subset script f of Cxy is equicontinuous under D, then f is totally bounded under the uniform and submetric corresponding to D. To prove the lemma, since X is compact, then the submetric rho is defined on Cxy. Total boundedness under rho is equivalent to total boundedness under rho bar. For whenever epsilon is less than 1, every epsilon ball under rho is also an epsilon ball under rho bar, and conversely. Therefore, we may as well use the metric rho throughout. That means there is no harm if we consider the metric rho throughout the proof of this lemma. Assume that script f is equicontinuous. We have to prove that script f is totally bounded under the metric rho. That means we have to prove that given any positive real number epsilon, we can find a finite subset of script f, say f1, f2, fk, such that b f1 epsilon comma b f2 epsilon up to b fk epsilon cover script f. That means we have to find a finite epsilon net of script f. For this, let us set delta is equal to epsilon by 3. Given any a belongs to capital X, there is a corresponding neighborhood ua of a such that distance of fx from fa is strictly less than delta for all x belongs to ua and for all f belongs to script f. Now cover capital X by finitely many such neighborhoods ua for A is equal to A1, A2, AK denote UAI by UI, then cover capital Y by finitely many open sets V1, V2, Vm of diameter less than delta. We can do this because capital Y is given compact. Let J be the collection of all functions alpha from the set 1, 2 up to k to the set 1, 2 up to m. That is, we can say that J is the set is equal to 1 to m to the power the set 1 to k. Now, given any alpha belongs to J, if there exists a function f in capital F such that f of ai is contained in V of alpha I for each I is equal to 1 to k, choose one such function and label it by f of alpha. Then the collection f of alpha indexed by a subset J dot of the set J and is thus finite. We claim that open balls B rho f alpha epsilon for alpha belongs to J dot cover script f. To prove this, let f be an element of script f. For each I is equal to 1 to k, choose an integer alpha of I in 1 to m such that f of ai belongs to V of alpha I. Then the function alpha is in J dot. We assert that f belongs to the ball B rho f alpha epsilon. Now let x be a point of capital X. Choose I so that x belongs to ui. Then we have the following inequalities. Distance of fx from f of ai is less than delta. Distance of f of ai from f alpha of ai is less than delta. Distance of f of alpha ai to f of alpha x is less than delta. The first and third inequalities hold because x belongs to ui, and the second holds because f of ai and f alpha of ai are in V alpha of I. We conclude that distance of fx and f alpha x is strictly less than epsilon, because this inequality holds for every x belongs to capital X. We have that rho of f alpha is equal to maximum of distance of fx to f alpha x, which is less than alpha. Thus, f belongs to B rho f alpha epsilon as asserted. This completes the proof of this lemma. Now, we are in a situation to prove classical version of Ascoli's theorem, which says that for a compact metric space, the script f subset of CXRN has compact closure if and only if it is equicontinuous and totally bounded. We have proved our necessary lemmas. Now we shall go to the proof of this theorem. Let us go to slide presentation. Let X and Y be two metric space where the metric of Y is D, and let script f be a subset of the function space Cxy. Then script f is said to be pointwise bounded under the metric D if the subset script f a is equal to f a such that f belongs to script f of y is bounded under D. That means the collection f a such that f belongs to script f, this is a bounded subset of capital Y. You can easily observe that any finite subset of Cxy is pointwise bounded at any point of x belongs to capital X. So now we prove our promised Ascoli's theorem. Let capital X be a compact space given Cxrn, that is all continuous functions from x to Rn, the corresponding uniform topology. A subset script f of Cxrn has compact closure if and only if script f is equicontinuous and pointwise bounded under D. We shall not prove this theorem in details, but we shall prove it by saying some steps of this proof. Since capital X is compact, the submetric rho is defined on Cxrn and gives the uniform topology on Cxrn. Throughout, we shall denote the closure of script T in Cxrn by script G. Step 1 of the proof. It happens that if script G is compact, then script G is equicontinuous and pointwise bounded under D. Since script f subset of script G, it follows that script f is also equicontinuous and pointwise bounded under D. This proves the only if part of the theorem. Now, step 2. We can show that if f is equicontinuous and pointwise bounded under D, then so is script G. In fact, denseness of script f in G will work for this. To verify pointwise boundedness given A, choose capital M so that diameter of script f is strictly less than capital M. Then calculation shows that M plus 2 is a bound of script f A. Step 3. We can show that if script G is equicontinuous and pointwise bounded, then there is a compact subspace Y of Rn that contains the union of the sets G of X for G belongs to script G. Choose for each A belongs to capital X a neighborhood UA of A such that D of GXGA is less than 1 for each X belongs to UA and G belongs to script G. Since X is compact, we can cover capital X by finitely many such neighborhoods, say for A1, A2, AK, because the sets GAI are bounded, their union is also bounded. Suppose it lies in the ball of radius capital N in R to the power n, centered at the origin. Then for all G in script G, this set G of X is contained in the ball of radius n plus 1 centered at the origin. Now let Y be the closure of this ball. Step 4. We prove if part of the theorem in this step. Assume that script F is equicontinuous and pointwise bounded under D. We show that G is complete and totally bounded under rho. Then G is compact. Completeness is easy, for it is a closed subspace of the complete metric space CXRN rho. Let us verify total boundedness. First, step 2 implies that it is equicontinuous and pointwise bounded under D. Then applying step 3, we can say that there is a compact subspace Y of Rn such that G is contained in C of xy. Equicontinuity of G now implies that G is totally bounded under rho as desired. This completes the proof of classical version of Ascoli's theorem. Now we have the following corollary of Ascoli's theorem. Let X be compact and D denote either square metric or Euclidean metric on Rn. That is, Rn is considered with the product topology. Now give CXRn the corresponding uniform topology. A subspace script F of CXRn is compact if and only if it is closed bounded under the submetric rho and equicontinuous under D. This is the analogous result to Bolzano-Foster's theorem. Here we are saying that a subset is compact if and only if it is closed and bounded and the additional condition is equicontinuous. For the proof, if script F is compact, it must be closed and bounded. The preceding theorem implies that it is also equicontinuous. Conversely, if script F is closed, it equals with its closure. If it is bounded under rho, it is pointwise bounded under D, and if it is equicontinuous, the preceding theorem implies that it is compact. Hence, we have our required result. So ultimately we have got a theorem in Cxy which is analogous to Bolzano-Weierstrass theorem. This is called Ascoli's theorem of classical version. With this we end this module. Let us pass to another module.